Hi, I'm Andy and this is question 6 on the AQA Decision 1 paper from June 2008. For more questions on this exam paper, click the eye in the top right corner. In question 6, we're told a factory makes two types of lock, standard and large, on a particular day. On that day, we're given various constraints about the number of locks that can be made, and we're given some decision variables that says the factory makes X standard locks and Y large locks, and we're given some information about the cost to make each lock. And we're told the manager of the factory wishes to minimize the cost of making the locks. And in part A, we're told to formulate the manager's situation as a linear programming problem. And so here's the information we need to get started. Our decision variables here, where X is the number of standard locks we make and Y is the number of large locks we make, and some information which will allow us to form some constraints. So we're told the maximum number of standard locks the factory can make is 100. Well, if the number of standard locks is X, that tells us that X must be less than or equal to 100. And the maximum number of large locks the factory can make is 80. That tells us that Y must be less than or equal to 80. The factory must make at least 60 locks in total. So the total number of locks, we would get that by doing X plus Y, and that must be greater than or equal to 60. And the factory must make more large locks than standard locks. That means that Y must be greater than X. For the final constraint, we're told each standard lock requires 2 screws and each large lock requires 8 screws. And on that day, the factory must use at least 320 screws. Well, if each standard lock requires 2 screws, then to make all of the standard locks, we would need to do 2 multiplied by X, and that will be the number of screws required. And then for the large locks, if we need 8 screws for each and we make Y locks, we would need 8 multiplied by Y screws to make those, and that must be greater than or equal to 320. This one can be simplified. Dividing through by 2 gives us X plus 4Y is greater than or equal to 160. So we've got 1, 2, 3, 4, 5 constraints. We're also going to need an objective function, and we're told that each standard lock costs £1.50 to make and each large lock costs £3 to make. So if we make X standard locks, we would need to do £1.50 multiplied by X, and if each large lock costs £3, that would mean £3 multiplied by the number of large locks we make. As this is a cost, we'll call our objective function C, but it doesn't really matter what letter you use. So this is all the information we would need to formulate our linear programming problem. One last thing we should perhaps mention here is that we are going to minimize this function. In part B, it says on figure 1, draw a suitable diagram to enable the problem to be solved graphically, indicating the feasible region and the direction of the objective line. So the first thing we're going to do is draw our constraints onto the diagram. Starting with X is less than or equal to 100, that's going to be a horizontal line that goes through 100. And we're interested in the region that's all to the left of that, so we shade the region that we don't want. Next up is Y is less than or equal to 80. That's going to be a horizontal line through 80. And we're interested in the region below the line, so we shade out the bit above the line. Next, we've got X plus Y is greater than or equal to 60. These type of lines are usually easiest to draw by plotting points on the axes. So when X is 0, that would mean Y equals 60, and when Y is 0, that would mean X equals 60. And we are interested in the region that is above that line because it's X plus Y is greater than or equal to 60. That means we shade out the region below the line again. The next line is Y is greater than X. For this one, you need to be careful because it's a strictly greater than inequality, which means you should draw it as a dotted line. So Y is greater than X, provided my scale is the same on both. It's just a 45-degree diagonal line that goes from corner to corner here. And as Y is greater than X, we're interested in the region where the Y values are bigger, which is above the line. That means we shade out the region below the line. For the final constraint, x plus 4y is greater than or equal to 160, we can't really draw it using the standard cover-up method. We can get one of the coordinates because we can say, right, if x equals 0, 4y equals 160, and that will tell us that one of the coordinates would be 0, 40. But the problem lies with the fact that if we do y equals 0, we get x equals 160, which doesn't fit on our graph. So all we need to do is choose an x value or a y value and see what the corresponding value would be. So we know that 0, 40 is on our graph, but we don't want to go too far out here. So let's say what happens when x equals 80. That would give us 80 plus 4y equals 160. Subtracting 80 from both sides gives us 4y equals 80, and dividing through by 4 gives us y equals 20. So we can plot the point 80, 20. And then we can draw a line from 0, 40 that goes through that point and continues on for the rest of the graph. We're interested in when x plus 4y is greater than 160, so we want the region above the line. That means we shade out the region below the line. So our feasible region is in here. Next, we need to draw our objective line. I'm just going to rub out this bit of working out here to make a bit of space. We need to draw any line where something equals 1.5x plus 3y. So there are infinite possible answers for this, but as we might need to use our objective line to find the minimum cost, if we can choose a sensible value for c, it will make our lives easier in the long run. Now there are many ways you can draw an objective line, and the way I'm going to show you is just one of them. What I'm going to do is start off just by having a guess for a sensible value of c, and I want a number that 1.5 and 3 both go into. That will mean I have whole numbers on my axes, and a simple answer to that would simply be, well, they both go into 6, so I could say let c equals 6, and then we get 6 equals 1.5x plus 3y, and we could then figure out what the coordinates would be to go on this line. We would get 0 something and something 0. So when x equals 0, 3y equals 6, that would mean y equals 2. And when y equals 0, 6 equals 1.5x, that would mean y equals 4. Now clearly this would be a very, very small objective line, and it would make sense for us to make it bigger. Well, 0, 2 is a bit silly, but 0, 20 would be sensible, so let's just multiply everything by 10. Let's let c equal 60. The effect that will have is to make these coordinates 10 times bigger. So rather than 0, 2, we would get 0, 20, and we would get 40, 0, which is a sensible sized objective line. I'm going to draw the objective line in blue so it stands out. It needs to go from 0, 20 and through 40, 0. One extra thing you can do to make this objective line stand out is turn the ends into arrows, and you definitely must label it OL, standing for objective line. In part C it says find the values of x and y that correspond to the minimum cost and hence find this minimum cost. So I'm going to use my objective line to find the minimum cost. To do that I need a 30 centimeter ruler, and I need to take my ruler and align it with my objective line. And then I'm going to move my ruler up until I find the first point where it enters this region. And if I do that, it's quite close, but it's going to be this point here. And that will be the minimum cost. Now, if you can just read off this value from your graph, particularly in questions where they draw it, that's great. Just write down the values. If you're confident you've got them correct, it will save you time. If you're not, what you need to do is figure out which two lines intersect and solve for the intersection using simultaneous equations. So this line here is x plus y equals 60. And this line here is my x plus 4y equals 160. If I call this equation 2 and this equation 1, I can subtract 1 from 2 to give me 3y equals 100, and y equals 33 1/3. So actually I couldn't read it nicely off the graph, and it was a good idea to do the simultaneous equations. Now that we know y is 33 and a third, we could sub that into either of these equations and we could then find out what the value of x will be. So if we sub y equals 33 and a third into number 1, that will give us x plus 33 and a third equals 60, which means x equals 26 and 2/3. But remember in the question, x and y represent real things. X represents the number of standard locks, y represents the number of large locks. So it makes no sense having a fractional answer for any of these. So what we need to do is find what would be the best whole number to minimize costs. In order to help illustrate what I'm going to do next, I'm going to draw this on Desmos, which you wouldn't be able to do in your exam, but will help you understand what's actually going on. So this purple line here is one of my constraints, and the blue line is one of the others. And the objective line is in black here, which I'm going to move, but it's going to stay parallel to this line here. So what we've done so far, as the objective line moves up towards the feasible region, we have found this specific point here, which if we were allowed decimal answers, we would have a minimum cost of £140. However, because we don't have decimal answers, we will have to continue moving the objective line past that point until we reach a whole number that is within this region. And if we do it, you can actually see that there are 2 points where you could do that. There is one here and one here. Obviously in the exam it'd be very difficult, even with the use of a graphical calculator, to find that out for yourself. So we have to use a little bit of trial and error. Remember, this point here is x is 26 and 2/3, y is 33 and a third. What we're going to do is try whole number points around here, first of all to check they satisfy the constraints, and if they do, second of all to see which one gives the minimum cost. So imagine our point is within the grid lines here, and the constraints we need to satisfy with our points are x plus y must be bigger than or equal to 60 and x plus 4y must be bigger than or equal to 160. So the point below and to the left here would be 26, 33. Now as that's both below and to the left, that's not going to be in our region, and we could check it here because x plus y is not greater than or equal to 60. But we've got a point here which is 27, 33, which may or may not be in the region, and we've got a point here which is 26, 34. Now these would make sense to be the first ones to check because they are the closest here. Because if the constraints are valid for one of these, there's no point in trying a point here because both the x and the y value will be bigger and therefore the cost would be bigger. So let's try 27, 33. If we put it into this equation, 27 plus 33 does equal 60, so it's valid for the first constraint. But if we do 27 plus 4 lots of 33, we get 159, so it's not valid for the second constraint. So we're not allowed to have this one. So let's next try 26, 34. Once again, it satisfies the first constraint because if you do 26 plus 34, you're going to get 60. So let's try it with the second constraint. If we do 26 plus 4 lots of 34, that gives us 162, which does satisfy the second constraint as well. So this one is alright. So that means it's definitely worth checking whether this one gives us the minimum cost. So considering we know that 2634 is within the feasible region, there is no point in trying larger y values with 26 because they'll definitely give a larger cost, and there's no point in trying larger x values with 34 because they will give us a bigger cost. So there's no point in going in this direction or this direction. However, there may be another point that we should check as well first, and that is the case where maybe the y value isn't 34, maybe it's 33. So over here we could possibly have 28, 33, and that would be worth checking. If we do x plus y, then we're going to get 61, which it's valid for. And if we do 28 plus 4 lots of 33, that gives us 160, which means this one is valid too. In a similar fashion to this point here, there's no point in trying 28 with any larger y values or any point in trying 33 with any larger x values, so one of these 2 points should hopefully give us the minimum cost. So remember, our objective function is c equals 1.5x plus 3y. Let's try it for these. This would give us 1.5 times 26 plus 3 lots of 34. That gives us a cost of £141. For the other point, we would have c equals 1.5 times 28 plus 3 lots of 33, which again gives us a cost of £141. So the minimum cost equals £141. And that is either at x equals 26, y equals 34, or x equals 28, y equals 33. You don't need to give both answers, either one of these would be fine. Going back to the graph just to make sense of that, if we increase our line, we can actually see the first integer values that are within the feasible region are here and here, which makes sense why there is 2 values.